Okay, so in these two videos we're going to have an introduction to the concept and ideas behind the integral, and more specifically geometrically, how does it relate to the derivative. So we expect you to know a little bit about the derivative. We're going to be focusing exclusively on the geometric idea of differentiating a function. So when we draw a picture of the derivative, what is the picture of the function going to look like? And we're going to talk about how differentiating is one thing, and we can actually do the opposite of that, and that's called the anti-derivative or anti-differentiation. And this is another word for integrating, or the integral. So in the second part, we're going to talk a lot more about this anti-derivative or the integral, and we're going to talk about how this represents area under a curve. So just like the differential tells us about the slope of a gradient, slope of a function, the antiderivative will tell us about the area under the curve. And this is actually a result from the theorem called the fundamental theorem of calculus. So let's start up here. So I've just graphed a function. Let's call it f of x. And I want to look at what does the derivative, if I drew the derivative, what would it look like? So we don't actually need to do any computations, x squared plus or minus 3, and then derivative. We don't need to do any of that. All we're going to look at is the function and its derivative, and this picture is going to tell us about this function here. In what sense? Well, when we take the derivative, we get df dx. Well, what does this really mean? It means when we change, so d represents a change, when we change x, how does f change? So that is really the slope of the function. If we change x, say from here to here, then the function goes from this height to that height. It decreases. We can see that it decreases slightly. Okay, so how do we represent that with the derivative? So we say because f is decreasing, the slope is negative of the tangent line. If the slope is negative in the derivative, well, what's negative about the derivative? It's the height. So its x value, the derivative will have negative height. And it will continue to have negative height whenever our function has negative gradient. And that occurs until it gets to, looks like that's at x equal to 0, it has 0 slope. So it's gone from having negative slope to 0 slope, which is going to be represented by the fact that the derivative will go from negative height to 0 height, and it'll happen at the same x value. Now it's flipped. Now we can see if we drew a tangent line, that is if we just got a ruler and just touched the edge of the curve, the ruler would be going uphill, or it's going to have positive gradient. Now again, gradient or slope of tangent lines to this function is represented by height in the derivative. So again, this is going to be positive height. For positive gradient, positive height. And we can see it's going to look pretty much straight, something like that. Okay, so far so good. Well, what if we had just started with this line and I said, what function, or is there a function out there for which when I take the derivative, I get this line here? Well, I could have done that. I could have just eventually worked out that it was this. I would have had to have done everything in the opposite manner, but I could have done it. Well, let's see, are there any other ones? Is this the only function for which when we take the derivative we get this line? Well, let's just try another one. Let's try similar shape, but let's actually put it in a different color. So let's try shifting it up. So it's going to be the same function, but it's just going to be shifted up a bit. So this is x squared just now. So let's call this orange one f of x. So it's going to be the same function, but it's going to be shifted up by some constant c. Okay. Well, let's see. Here it has the same slope. It's 0. So it'll also go through here. And if we look at this point here, the slope is also positive, and because it's only shifted up, it'll have the same slope as our original function. So again, it'll have the same height. It's negative slope, negative height. Okay, and the same thing goes for here. So how is this represented algebraically? Let's look at that quickly. So what we're doing is we're saying that df dx is actually equal to this one here. So let's see how that works. So we take the derivative algebraically. We have f of x plus c. Maybe you can see where this is going. This multiplies through the bracket, so we end up getting df dx. But then we're left over with this extra term, dc dx. Now c is just a number. So how can we represent dc dx? Well, c is just a number. Let's say c is 2. Then that's represented by y equals 2. Okay, so how does c change, which is just this line? How does this line change the height as we change x? Well, it doesn't. It just stays put. It's got 0 gradient. So this is equal to, this is 0, and therefore we get our df dx. Okay, so that's the geometric idea behind why the derivative of a constant is 0. And so this is going to tell us something interesting about when we go in the opposite direction of doing the derivative, which is called taking the antiderivative, then we actually have an infinite number of choices. Again, I could have drawn, well, anything really, as long as it had the same shape, but it's just shifted up and down. Okay, so we've got an infinite number of choices when we go up the way, but we can do it. So why don't we now ask the same question, but up here? So what we're going to ask for, so we're going to say that we can do it in the opposite direction. Let's actually do it. So we're going to ask for a function, we'll call it big f of x, for which when we take the derivative, we get this function. Okay, so we're going to do the opposite of what we've done down here, because I said we could do it, so let's actually do it. So remember that the slope of the function is represented by the height of the derivative. So what we're going to look at is the height of this function, and we're going to correlate that to the slope of this function up here. Okay, so here we have positive height. So here we're going to have positive slope. But again, where can I put this? Remember, we have an infinite number of choices, so we can put this anywhere. So I'm just going to make a choice to put it here. Okay, so positive height, positive slope. So that's going uphill. That's great. Now, this is crucial. So this is the important part. This has 0 height. Remember, 0 height correlates up here to 0 gradient. So we need to make sure it's at the same x value, so it's going to level off just about here. Okay, here it continues to have negative height, which means we have negative gradient. So for all these values, in fact, all the way up to here, it's going down. So we're going to represent that by that. Now here again, this is the second crucial point, stationary points they're called. So this is where the derivative is 0. That means that the function has 0 slope. So I'm going to represent that by this here. Here is positive height, so positive slope. Okay, so filling this in, we've got all the information we need to draw something like this. Something like that. Okay, so we can do a little check and we can see that at each point the slope is represented by the height of this function. So here, positive slope, we have positive height. 0 slope, well, we have 0 height. Negative slope, negative height, that's all good. And then here we have 0 slope, and this correlates to 0 height. And then again, the same here, positive slope, positive height. Okay, so algebraically, what have we just written? We've asked for a function, f of x, that's what we called it, such that when we do the derivative, that's what we did here, we get our original function, f of x. That's what we've asked for. And if this is the case, so if this big f of x is out there, if we can write this, then f of x is called the anti-derivative of f of x. Okay? Now again, remember, we could have made a number of different choices. As long as it had the same shape, it would have just had to have been shifted up. So it would have been just the same shape, but just shifted up. Because again, when we take the derivative of a constant, it goes away and becomes 0, just like it did here. Okay, so in the next video, I'm going to talk about why do we care about this thing called the antiderivative. So just like the derivative tells us about the slope of a function, the antiderivative is going to tell us some very useful information about this f of x, and it's got a lot to do with the area under the graph of f of x between x equal to a and x equal to b, so two values. We're asking for the area under the graph. Well, this is where this antiderivative becomes so important and so useful, and that'll be in the next video.